Okay, welcome everyone. We're doing a deep dive today, really focusing just on one source.
That's right. And it reveals this, well, quite interesting intersection between math concepts and a biological process.
A very specific one. The source talks about using calculus to look at the rate of disease spread in poultry.
But not just any poultry.
Exactly. Poultry fed with grain from agricultural harvest. That's the specific context
So
given.
it's applying this, abstract math tool to understand how fast a disease is actually moving through these birds.
Right. So what we want to do is sort of unpack that. What does using a derivative mean here in this disease context?
Hmm.
And why focus so much on this specific setup, the poultry, the grain, the agriculture link?
Well, fundamentally, a derivative, it just tells you how quickly something's changing right at a specific moment.
Okay.
In epidemiology, understanding that speed, that pace of an outbreak is, well, it's crucial.
So it's not just how many birds are sick, but how fast that number is going up or down.
Precisely. That rate, that instantaneous speed, that's what the derivative captures. It's
Yeah.
like the speedometer for the sickness, as you said.
Got it, a speedometer. So how does that math tool actually work when you're modeling disease in a population like this?
So you often see these models, like the AIR model, susceptible, infected, recovered.
Yeah, I've heard of those.
Derivatives are like the engine behind them. They describe the rate people or birds, in this case, move between those groups.
Ah, okay.
So the derivative of the infected group shows how fast that number is changing. And that depends on things like, how easily the disease transmits.
Right. So the derivative helps measure that transmission speed, how quickly healthy birds become infected ones. But then this grain part,
Yes.
why does the source bring in the agricultural grain? How does that connect to the math?
Well, that's where the context becomes really significant. It's not just general disease spread.
Hmm.
It's potentially linking that spread rate back to their feed source.
Suggesting the model itself, the math, actually includes variables about the grain.
Exactly. It could be things like maybe the grain quality.
Hmm.
Does that affect the bird's immune systems, make them more susceptible?
Interesting. What else?
Or, maybe contaminants, things getting into the grain during harvest or storage.
Hmm.
That could affect how severe the disease is or how easily it spreads.
Okay.
Even just like physical factors related to the feed consistency, dust, how the birds cluster around feeders,
Yeah.
maybe those link back to the agricultural source and influence the transmission rate.
Ah, I see. So the derivative isn't just calculating some generic rate. It's calculating a rate that might actually go up or down, depending on factors tied directly to that grain.
Precisely. The number you plug into those derivative equations, the parameters that define the speed, they could be statistically linked to, say, the batch of grain or the farming methods used.
So using the derivative lets researchers actually put a number on it, quantify how sensitive the disease spread speed is to changes in these grain factors.
Yes, exactly that. It moves it beyond just, oh, feed might matter, to feed quality dropping by X amount could increase the transmission rate by Y% per day, something quantifiable.
That feels pretty powerful. It connects the math directly to, well, practical farm management, doesn't it? Biosecurity, maybe even deciding where you source your grain from.
It really underscores how quantitative methods help us understand these complex biological systems in their specific environment. Focusing on the rate gives you predictive insight.
Okay, so let's wrap this up. We've seen our source use a core math idea, the derivative,
Right, the rate of change.
to specifically look at the speed of disease transmission in poultry, but tied directly to this context of them eating grain from agricultural harvests.
And it really highlights how these, abstract concepts from math class find very real, very concrete applications. Farming, animal health, that gives real insights.
So here's something to think about, just based on what the source implies about these connections. If a tool like the derivative can help untangle the dynamics between agriculture, animal health, and disease speed, where else might simple math tools reveal surprising connections and rates of change in the complex systems all around us? What other hidden dynamics could they uncover?